Hello, Chemistry 30 people. Continuing on here, a model for reaction rates part 2. Last time we talked about collision theory and 3 specific things about collision theory. Reactants must collide is the first one. Kind of the obvious one. Collide in the right fashion, just like the demo derby. To make a successful collision, must collide in the right way. Same thing with chemistry. And this vodcast is going to look at the energy side of it. Collide with sufficient energy. And look at that in more detail. And with that, brings up the idea of activation energy. And that is somewhat the minimum amount of energy required for a reaction to occur. That minimum amount that I need to make a reaction successful. So activation energy, we'll take a look at that. And there's a nice little way of looking at that in terms of a diagram, a graph, if you will. Here's one right here. So this is basically a graph of energy versus progress. So it shows the energy that's involved as time passes. The R represents our reactants, and the P represents the products. So we can look at a few different things here. If I look at this little area here, I'll call it number 1. Number 1 there represents the energy that the reactants have. Or we could refer to as the stored energy, the potential energy of reactants. So I'll shorten the words potential energy just to PE. Don't get it confused with the Z. Looking over here, I have this over here, which of course represents the potential energy of products. The amount of stored energy that the products have. Okay? And of course I have this, you may have noticed this big hill here. So this was number 2. I could call this number 3. That represents the potential energy of what is referred to as the activated complex. So what happens is that the reactants come and collide with each other and for a very short time form kind of a supermolecule, if you will. Very short-lived, and it's a complex thing. It's very short-lived. What could happen is that it could just simply break apart, form reactants again, or it could continue on and form products, which is what we would hope for in a successful reaction. So that would be the potential energy that that activated complex has. If I change the color here, I'm getting kind of messed up. If I look at this amount, call that number 4, that represents the activation energy of the forward reaction. So that is that minimum amount of energy that the reactants need to have in order to form the activated complex. And in this reaction, you can see it's a fairly large amount. One final thing we can get from this diagram, if I just extend this line, we have this. Number 5. So it's the difference between the height of the reactants and the height of the products, and that difference in energy we looked at in the last section there, that is actually the change in enthalpy for the reaction. And you can see here that it's going up, a positive energy amount, and of course that implies an endothermic reaction. So I'm just going to write that in brackets. Endothermic reaction in this case. And you'll see that with endothermic reactions we have a high activation energy. We have to supply a lot of energy to get those reactions to happen. That outside energy coming from the environment or from some other way. a similar diagram, except I somewhat reversed it. And of course, this represents the opposite. In this case, I have the same things here: potential energy of reactants, potential energy of products, potential energy of activated complex. I have my activation energy right here. I'll symbolize that as AE, activation energy. And if I continue that line, take a look here. The difference between reactants and products. So I have high energy reactants, lower energy products. I have this extra energy which is going to be released. And you can see that is a delta H. That's the enthalpy of reaction. In this case, it's negative. And of course, that implies an exothermic reaction in this case. So these potential energy curves are very efficient at showing many different things here. 5 items here: the potential energies, the activation energy, the potential energy of the activated complex, and kind of relating it back to the last unit too, the enthalpy of the reaction, whether we need to supply it in, or lower energy reactants going to high energy products, or whether we don't need that extra energy, it's simply released because we're forming lower energy products.